Okay, hello. Today I'm going to talk a little bit about small scale model qualification or verification, specifically for downstream unit operations. Um, there's a lot that goes into this topic. We're not going to cover all of it because I'd say there's too much. I'm just going to talk about some things that kind of popped into my head. This is something that I've been working on recently at work and thought it might be nice to just share my thoughts on it and like kind of what I've experienced. Definitely not an expert. It's just, I guess, what I've kind of picked up and, um, started to think about uh, small scale model qualification or verification. So, I guess first, what is the goal of small scale model qualification or verification? Um, Those two terms I wouldn't call interchangeable. We'll talk about them in a little bit, but you might hear me use them interchangeably in this video. So the goal is to prove that your small scale model is a suitable representation of your at scale process. And why do you want to do that? It's so you can run small scale experiments and draw conclusions from that data for the at scale process. So that means, if you can show your small scale model is a suitable representation or equivalent to your at scale process, you can run experiments in your PD lab at the lab bench and say, hey, if we do this, the large scale, we'll get the same result. It's important for process characterization, um, where you might start to define parameters as critical process parameters, as CPPs, or key process parameters, KPPs, if you use that term. I know not everyone does. Had companies where we did use KPP and others where we didn't. And then eventually, this will roll into or help define a control strategy. So, it's definitely important. Um, so now I've noted verification and qualification, right? So these, I've seen them used differently, right? Qualification, um, we call, or like in my experience, we call qualification is more robust. Um, you'll define, equivalence, or we'll call it qualification criteria prior to running experiments. And then we'll also say that there's robust statistical methods used. And yeah, no, I'd say like no order of importance here, but these are like a few things that we would require, in my experience, for qualification. In general, it's just like a more robust way of doing things. The verification, this is less robust and more, I'm just going to call it more on the fly. Um, Maybe you have weakly defined verification criteria. Um, Verification could rely more on the SME, that's you, on your judgment on if things are similar, and maybe, yes, way up there. Maybe maybe you'll use stats. And yeah, so in short, qualification's more robust. You're going to write a protocol beforehand that says, hey, for this unit operation, here's what we're doing, and these different responses, call it recovery, process time, monomer, they need to be within this margin and the margins will be defined based on some different criteria, but we'll talk about that shortly. So when you're doing your small scale model qualification or verification, there's a couple things you're going to look at. Say the first thing you're going to want to do is get your descriptive statistics. Descriptive statistics. So this is going to be, you're going to calculate means, min, max, standard deviation, median, that kind of stuff. Next, you're going to do qualitative analysis. So for chromatography, you might overlay your chromatogram for the different scales, flux profile overlay, maybe pressure trends, scatter plots of the different responses, like that you use to calculate your descriptive statistics. Those are really useful. Control charts, that kind of stuff. You're going to start looking at the data as well. And then there's also your statistical testing, and I'm specifically going to talk about different hypothesis tests today. Specifically the t-test and toast. I know there's like other tests like the f-test for, I think that's for your variance. We're not going to talk about that today. I know people use it. I've never used it. Upstream, uh, time data. Well, I'm blanking on the correct word from that. But like if you have like cell density in your culture over time, I know people use principal component analysis and some stuff like that to show that these trends are the same. I've never done that. We're going to talk about this t-test and toast test a little bit more today. So I'm going to just share screen, and we'll look at the hypothesis for our t-test and our toast test. Talk a little bit about those. Okay. So hopefully you're seeing Excel. This is where I have the null hypothesis for the t-test, where here you're saying the null hypothesis is that the mean of your small scale is equal to the mean of your at scale, with the alternative hypothesis as the means aren't equal. So in this instance, right, if you reject your null hypothesis for, small p values, whatever your threshold may be, 0.05 is often used. If you reject your null hypothesis with p values less than that, you're saying that the means are different, which obviously we want to show that they're the same. So here you want to have large p values and essentially fail to reject the null hypothesis here. And, by doing that, you're pretty much saying that, you can't say that they're different means. So yeah, I mean, this is one way of doing things. It's not preferred. There's a couple things about this I don't have, I guess, great reasons for you, but one is that you're not actually like proving anything. You just can't disprove something when you do the regular t-test. You're not proving that the means are equal. You're just not if you fail to reject, you're just not able to say that they're different. So that's definitely a drawback. There's definitely a better way to say that, but I hope you get the point. And then the other thing about this is when you're doing small scale model verification, qualification, oftentimes you don't have a whole ton of runs like at scale or the small scale. I mean, there's always this rush to get things done and you don't have all the data you want. And with the t-test, your like the power is pretty weak with small n, small number of replicates. So like here, it's actually really easy to fail to reject the null hypothesis with small n. So like, if you only have three at scale runs and, three or six small scale runs, it's pretty easy to fail to reject this t-test and then claim that they're the same when really they might not be. Likewise, if you have large n, if you have a lot of replicates, it becomes really easy to detect small differences between the different scales, and you might then reject your null hypothesis and not be able to say that the two scales are the same. So then we have this other test. This is like the gold standard. At least that's my understanding. You want to do a toast test. It's equivalence test. It stands for two one-sided t-test. And here, the reason this is so nice is here you're saying for the null hypothesis is that the difference between the means at scale is greater than some theta or like some equivalence margin, or the difference is less than that equivalence margin. So pretty much you're starting off here saying like the null hypothesis that you're different. They're different. The scales are different, or like the difference between them is larger than some theta. Um, and if you have small p-value, you reject the null hypothesis and you accept the alternative that no, actually the difference between scales is within your plus or minus theta, as you can see on with the H1 there, the alternative hypothesis. So that is already an advantage of the toast test. And then also with small n, it becomes harder to reject the null hypothesis here. So if you are limited for replicates and you're running toast tests and you're able to reject your null hypothesis, think that helps you there. It shows that, hey, there is something real we're detecting here. And then the last thing I'll say about it is you get to pick this theta and this equivalence margin. And I guess the question is, how do you do that? I think that this is where the qualification and the verification, my experience definitely differs. Is like with the qualification in our protocol that we write before we run any experiments, we define what theta is. And that theta is based off of historical data, specifically historical data that will not be included in the data set that we're running the toast test with. So that theta might be, one, two, or three times the standard deviation for a certain response of your like at scale historical data. You can also use things like, this is where like the SME judgment comes in a little more. I've used in the past, um, like the assay variability has been where we've defined our equivalence margin, or equipment capabilities. Those types of things definitely come into play for picking theta as well. So the last thing I guess we'll talk about in this video is like just this little example I made with some dummy data. So I'm going to share my screen again, and we'll go through some dummy data here. So hopefully you're seeing jump. I made up some like recovery percent monomer HCP. You can imagine a chromatography step here where maybe we're improving monomer and reducing HCP. We have 6 small scale model runs. These would be done at center point. And then we have 3 at scale runs. We're calling them Eng1, Eng2, and Eng3. And then we have 4 pilot scale runs, 50 liter. Now, one of the best companies I ever worked for, as far as like robustness and rigor for late stage process development work, we always had 3 to 5 pilot scale runs done at like this pilot 50 liter scale. And we were able to use those for defining our equivalence margins. That was super nice. You don't always have that. So then when we had our end runs, we could strictly use end runs, clinical runs for at scale data set. And then of course, run our small scale runs um, in parallel. Like I haven't talked about like satellite versus non-satellite runs. That might be something for another video, but here, the way I definitely like to do this is what will be these small scale runs will be satellite runs where we're actually getting material from these different end runs. So you could, imagine like maybe small scale one, run one and two came from Eng one. That's where we got the starting material. Runs three and four from Eng two, and then five and six from Eng three. So yeah, now to get into it here, the first thing we're going to want to do is, um, let's look at our historical pilot scale data where we're going to set these equivalence margins. I already ran this here earlier. So we have, means, usually the mean for each. We got these standard deviations, min, max. All of this is useful when qualifying or verifying your small scale model. Now I'm pulling up Excel again. Hopefully you see that. And we're going to calculate 3 times the standard deviation for each of our 3 responses, recovery, monomer, HCP. We'll use those as our equivalence margin. So you got 3.6 for recovery. Here's your standard deviation, by the way, if you can see my mouse. Also 3.6 for percent monomer, and then 403 for HCP. And that gives us these 3 times standard deviations for that we'll use for the equivalence margin. So that's these numbers here. So I'm using 3 times standard deviation. I mentioned this before that, if you're doing qualification, you're defining that beforehand. You don't have to use 3 times the standard deviation. Maybe use 2. Maybe you use like your equipment capability for detection. It could be whatever, but you define that beforehand in qualification, most certainly. So, next thing you might do, I talked about visualizing your data. So we can do that. I like these graphs here. Let me see if I can figure out how to do this. So analyze, quality and process, this variability and attribute gauge chart is nice. So let me see if I can make this the correct way at first. So we have our scale in the X grouping, and then I think run type in the sample ID here. Yeah, okay, this is what I wanted. Okay. So like here now, this is what I was talking about, like these scatter plots. These are very useful. You can see the value for each run, and then it's grouped by scale. And then you can do things like add the group means. So now you can see the means here. Maybe is there like an overall mean? Show grand median. You can start to visualize your data this way, which is nice. Looking at this, we can see there might be some difference with the small scale model. The recoveries seem generally lower than the at scale. For percent monomer, they're kind of all over the place. The range is pretty wide, 6%. And then the HCPs, again, they're kind of all over the place, but pretty similar. So yeah, I mean, this type of plot is very useful for doing your small scale model qualification work. You're going to want to include these in your report along with the descriptive statistics, so we can pull those up as well. I think variability summary report, maybe. Yeah, so here, like you have your mean, standard deviation, min, max, range, median, all those descriptive statistics we talked about that are Nice. And it has that for everything, your 2000 liter scale, your SSM. Um, yeah, you're going to want to have all that data in your qualification report. So then, okay, we had our equivalence margins here. We're using 3 times the standard deviation just because. Then we will check out some t-tests and some toast tests. So now we're going to make some more plots by scale. So this is kind of similar to what we were looking at before, but now all runs for a scale are plotted on top of each other. And we can start our hypothesis testing. So one thing I'll do first is let's just start with the t-test. You can run the t-test. See the t-test is in there now. So for like our recovery by scale, um, we're looking at our p-value here. We're over that 0.05 threshold. It's not significant, which is what we want, right? It's not significant. So with that null hypothesis being that the means are equal, we fail to reject. For percent monomer, we also are failing to reject. And then for HCP, we fail to reject, right? And like this kind of makes sense. You see there's like a lot of overlap. These don't seem very offset. The recovery, this plot seems to have a little bit of offset, but it's not a statistically significant difference. So now let's start doing our toast tests. There's all sorts of analysis you can do in here, right? The toast test is an equivalence test, like I mentioned. We can do mean, standard deviation as well. I think this is the F test. I can't really remember, but we mentioned that earlier. Okay, so here we're going to do equivalence test. You can do pooled variance where essentially you calculate the standard deviation, I think, with all the data. You can look that up on your own, like what it does to the test statistics. They're a little different when you calculate like a pooled standard deviation. I'm going to say that they're unequal variances. In my experience, the small scale models generally have tighter uh, distributions of data, smaller standard deviation or smaller variance. That's just been my experience. I don't know that this data set doesn't necessarily show that because I just made it up before this video. But anyways, so we're going to do unequal variances. And then for recovery, we had our standard deviation was 3 times the standard deviation was 10.8. So I'll click OK. All right, so now we have our toast test results. You can see like these are the hypothesis that we're testing. And the forest plot is super useful to look at. You can see that this range has fallen outside of our equivalence margin. So, our maximum p-value is above that threshold, and we're not able to reject our null hypothesis. And these scales are not considered equivalent within our margin of 10.8%. So now let's just say for whatever reason, we have huge variability in our means of measuring recovery. I don't know why that would be. Maybe it's a PCR method for testing genome copies of an AAV or something, and it's huge. And we have to say, no, we can do or 10.8% is too tight. So we're going to say we can only detect within 30%, plus or minus 30%. We're going to use that as our equivalence margin. Click OK. Oh, look, now we're within their equivalence margin. Our p-value is less than the threshold, and it's equivalent. So yeah, I mean, like that's where this equivalence margin is pretty important that when you set that beforehand. So we can just run through these other ones really quick and I guess then wrap up the video. So equivalence. For monomer, we'll do the means, unequal variances. The equivalence margin we're using is also 10.8. That was 3 times the standard deviation. And here, in this case, at that 10.8, we're well within the equivalence margin, and the p-value is below our threshold, so we're equivalent. And now we can check HCP. Equivalence test means. Now this variation was pretty big. 3 times the standard deviation was 1209. Remember, these standard deviations we took from the 4 50-liter pilot scale runs that I had. If you start using the data you're comparing against to come up with these equivalence margins, like using their standard deviation, I think you start to bias your testing. Mathematically, I don't really know what's going on, but if you can avoid that, you should. And here again, we are considered equivalent. Max p-value is below our threshold of 0.05. So yeah, I mean, those are just a few things that I would run through if I were doing small scale model verification. I hope that this video was helpful. Obviously, there's a lot that goes into small scale model verification or qualification, things we didn't talk about today, right? I talked a little bit about, or I mentioned like the satellite versus non-satellite runs, doing hypothesis testing on the variance between the scales. Um, uh, we started to talk a little bit about like the pitfalls of the t-test. Definitely look more into that, and like why the toast test is more powerful. And then for upstream small scale model work, I know that principal component analysis can also be used to show stuff over like time course data. So yeah, I mean, I think that this is just barely scratching the surface, but a few things that were in my head and I wanted to share with you. So hopefully you enjoyed the video. Share your thoughts in the comments if you have differing opinions, or if I, nailed something and you liked it, or whatnot. Just want to, hear your feedback. So, yeah, cheers and happy qualifying your small scale models.